in progress.
So this is the second lecture in the series of gravitational lensing. I hope you heard about gravitational lensing, the introduction to gravitational lensing and its basics yesterday by Surhud. So in this second lecture, we're going to focus more on strong gravitational lensing and its applications.
Got it.
Let's try now. It stopped again. So in strong gravitational lensing, what we usually see is that there is a source far away in the distant universe, and the light rays coming from the source on its way to the observer can get deflected into multiple directions because of the presence of a massive object in the line of sight, which could be like a galaxy or a cluster of galaxies, and the observer will see something like this in the sky. So what you will see is that there is this massive object which is in the center, and then there are all these gravitationally lensed images, multiple images of a background source, and in some cases these look like gravitational arcs. And so the main observables that we expect to see in strong gravitational lensing are the image positions of these multiple images, magnifications, and time delays. So let's just go through each of these different observables and refresh our mind how we can derive these. So as you remember from yesterday's lecture, so the way we can calculate these image positions are as follows. So suppose there is an observer here, and then there is some mass in the line of sight, and suppose at the large distance there is a source at a separate redshift plane, right? So in the absence of this any massive object, the light rays coming from this source can be seen at an angle theta. Can be seen at an angle beta. But now in the presence of this lens, what happens at these light rays, they get deflected from its original path, and we can see them coming at an angle theta. So that's what is shown here. Okay, and so what we can readily see is we can subtract this angle theta. We can subtract the angle beta from this theta, and what we get is this deflection angle alpha. But the true deflection angle is over here, shown by alpha tilde, and we can easily relate these two with the help of this impact parameter psi, which is at the redshift of the lens. And so this is the expression for this the deflection angle and the scale deflection angle, which is given by the angular diameter distances to the lens plane and also the source plane. And this is the lens equation, which allows us to readily relate between these angular positions of the source and the images. So some points to remember are these the angles that we're talking about. These are two-dimensional vectors. The distances which are shown here, these are the angular diameter distances, and the true source position is always an unknown. We will never know what is the true source position because the lens is there in the foreground, and the kind of distances we're talking about and the velocities of these objects are such that these systems are basically static, and so it doesn't really move or evolve much in our lifetime. So these systems look static, and so we never get to see the true source position of these distant sources. So and the positions that we can measure are obviously then relative positions, because all we can see is image 1, image 2, image 3. So we can always just measure the relative positions, and a good choice of our origin is the lens which is at the center of the system. Right, and so you may remember that Surhud talked about one of the first evidences in support of gravitational lensing, where they look at the deflection to the position to the stars during the solar eclipse, right? So those are the cases where you can see what is a true source position, because the sun is moving with respect to the background sources, right? But here we will never be able to see those kind of things. So here I'm just showing you one example of a gravitational lens. This is an image taken with the Hubble Space Telescope. Here what you're seeing is this massive galaxy, which is part of a galaxy cluster. And these multiple images that you can see here, these are of a distant quasar. And we can see even from the morphology that there is this bright source which is lensed multiple times. And you can also sort of see the underlying host galaxy, which is being also gravitationally lensed, which is a host of the quasar. Now moving to magnification. So magnification is something that so this is another observable. So as you may remember, what we can see is either an isotropic magnification or anisotropic magnification, which means so isotropic magnification would mean like the circle from imagine the source is a circle, then after lensing the size of the circle would increase, so that's coming from this convergence term, and an isotropic effect would come from both this convergence and shear term, which will cause squashing or stretching of the original source, which is circular, shown to be circular in this case. And this mapping between the source plane and the image plane is given by this Jacobian matrix, which is given as follows, like del theta over del theta. And so there are some more interesting properties that we can make note of in these cases. So for typical lens systems, the types of images that we expect to see are divided into these three categories: type 1, 2, and 3. So if you look at this Jacobian matrix and so the magnification, yeah, so basically the magnification is given by the image area over the source area. So if you look at these the eigenvectors of these Jacobian matrix and the eigenvalues. So the eigenvalues, they can have either a positive value or a negative value, and based on since we have two eigenvectors, we have two eigenvalues, and so there are different types of images that one can observe based on the values of the values of the eigenvalues, right? And so that is shown here with some pictorial representation. If both the eigenvalues are positive, then these images are called type 1. If both are negative, then they are called type 3. And if we have 1 plus and 1 minus, then these are called type 2 images. So just to show visually how that might look like, so this is an interesting property that one can get to see, and also is very informative in terms of understanding what kind of images we are looking at, and also get better idea of the lens model itself, which is as follows. So suppose you have a source which has some asymmetric feature in it, right? So that you can see like this, like a triangle which shows some feature in the source, right? And so if you are looking at a type 1 image, then it's basically a copy of the original source. It will just look like a scaled version of that same source. But now if you look at the type 3, where both the eigenvalues are negative, then it seems to be flipped by along x-axis and y, both directions. And so you can see this kind of change in the type 3 images. Whereas if you look at these type 2 images where only one of the eigenvalues is positive, there you can see that the source is getting mirrored only along one of the axes. So this is also another observation constraint which we can make use of to understand what kind of images we are looking at, and thereby understand better about the lens model. Right. So here there is another example of a lens system where we can look at. So this is also another galaxy cluster. You can see all these massive yellowish galaxies. They are part of this galaxy cluster. And very interestingly, there is a source which is a spiral, nice blue face on spiral galaxy, which happens to be lensed by this galaxy cluster. And you can see these highly distorted images over here, and also another very minimally distorted image. So if you do the analysis of this system, there are more images somewhere over here, not visible in this particular snapshot. But if you do the analysis of this particular system, what you will find that this is the one, this is the image, which is the type 1 image, which is basically, as I said, like it's just another scaled version of the original source. And then some of the other images, they are type 2 images and so on. But because this is so visually captivating and also gives a lot of information in the structure, we can see that a lot of information from the structure of the source itself. You can get very many constraints compared to any other typical lensed sources where you either see just a point source or just a single arc. You can get very many constraints from systems space where you can see all the details in the spiral galaxy. And also you can clearly see compared to this particular image, some of these images are distorted and magnified. So this is just an example to show magnification in the in a lens system. So the next observable are the time delays, and so the time delays. This is something that we can infer from the Fermat potential, where the one can see that there is a time delay between multiple images because they take not only because they take different amounts of not only because they traverse different amounts of paths, but they also experience different gravitational potential, and so that those are the two terms which go into calculating the time delays between the multiple images. So another like a very interesting application of this particular observable is through the measurement of these time delays, which are related to the potential of the system, and also the redshifts and the distances between us and the lens and the source, right? Because of these dependence, what we can do is that we can measure the time delays, and if we measure the redshifts, if we can model the lens system, then we can get constraints on some of the cosmological parameters like the Hubble constant. So in order to be able to measure these time delays, we need to have a source which is variable. So this is not something that is possible for usually for galaxies. If your background source is a galaxy, then these are pretty much static. So if you want to be able to measure these time delays, you need to have a source which shows some fluctuations. So these time delay measurements are only possible for sources that are variable or transient, unlike the image positions and the magnifications, which can be measured for all of your lens systems. And again, similar to the other observables, time delays are also relative. It's something that you can only measure as a relative quantity. Here, this particular animation shows observations of one lens system. So you can see that there are these 4 images, and you can see that after some time lag, this 4th image starts to become bright enough that it is observable. So there are these 4 images, and here in the bottom we can see the light curve measurements, which span a period of a year or so, showing how the source is fluctuating. And you can also maybe look at when we look at these light curves, you can see there is some characteristic features, like there is some fluctuation, but up to some point there is this characteristic feature. You can see there is a sudden brightening of one of the source, and the same feature then replicates in the other images after some time, right? So if we can measure these kind of characteristic features in the light curve, then we can very accurately measure the time delays, and then these kind of systems will allow us to measure get constraints on the Hubble constant. So this is just to again give some idea about the time delays and the different types of images that we see in these lens systems. So these different panels, they show the two-dimensional map of the arrival time surface. So we can imagine that there is a source which is here, and these different contours they tell you the arrival times from the light rays coming from this source. So this particular case, the L here stands for low. It doesn't stand for length. So when we say L here, it means it is a minimum in the time delay surface. And this is the case where there is no particular length in the foreground. This is just the source, which is at the minimum of this time delay surface. So this is what happens when you have no lens at all. But now if you introduce a lens, which is some massive object in the line of sight, then you can see how it starts to perturb this time delay surface. When the lens is sufficiently well aligned with the background source, then you have these different peaks or dips or locations which are called the saddle points in these time delay surface, which correspond to the locations of the images. So here L stands for low, H stands for high. So this is a maximum in the time delay surface, and then S stands for saddle point. So these are the locations where the gradient of this time delay which we showed in the previous slide. This is where it goes to zero. So these are the extrema in the time delay surface, and these are the locations where images are formed. The arrival time of the light rays. So any contour is a constant value of the arrival time from the
Now, what do the saddle points correspond?
These are the locations where the images are formed. So if you look at the topology of this time delay surface, it will be a saddle point, meaning in one direction there is a dip, and in the other direction there is a peak.
Is the brightness?
No, this is for the time arrival times. So this is for the time delay. So yeah, and so this is one case where three images are formed, and then this is another case where the lens model is such that, or the source and the lens alignment is such that you can form additional images. So here we have a pair of minima, and then a pair of saddle points, and then one maximum. So now let me talk about some other features that we see in these lens systems and how they can be, again, very informative to better understand the system. So these are called the critical curves and caustics. So these correspond to the magnification. So if you look at the magnification in a two-dimensional plane, in the lens plane, if we just calculate the magnification expected at each location, then there will be certain regions. So this is the image plane. The left hand side is the image plane, and the corresponding mapping in the source plane is shown over here. So if you look at these contours here, these contours correspond to that points, those points in the magnification map where the determinant goes to zero in the over here. I'm showing you. So the determinant goes to zero, and so and then the magnification, which is the inverse of the determinant, it goes to infinite. So any images which are formed very close to these critical curves, they have very high magnification. So you can see there are two sets of curves. One is this outer critical curve, and there's another one which is the inner curve. So these things, so as you can see, these are shown with different colors, and the corresponding mapping is shown here in the source plane. So green part of the critical curve maps to the green part of this caustics in the source plane. So now let's just focus on this right hand side, the showing the caustics, which corresponds to how these curves map in the source plane. So now you can imagine the source being placed, and also for reference, the lens is shown to be at the center. So So now you can imagine the source is you can imagine that the source is varying with respect to the line of sight and the center of the lens, right? So there's like different impact parameters you can imagine here. And so suppose the source is far away from the line of sight to the lens. So this is the region which falls in the weak lensing, where you only see some distortions of the images. And what we mean by one here is that there is only one image. There are no multiple images at this point. So when the source now starts to move closer and closer to the lens center, as it crosses this outer caustic, this is the regime what we formally refer to as the strong lensing, where you can now start to see multiple images. And this particular set of critical curves and caustics, they correspond to a specific model, which is like the typical elliptical galaxy. So that's the model I'm showing you. Based on some different mass distribution for a different lens system, the model can look different. But for typical galaxies, this is how the model would look like. So it's a good illustration and helpful example to understand how typical galaxies, how the mass distributions are typical galaxies, and what are the features one can see. So once the source crosses the caustics and it comes inside this outer boundary of the caustic, it falls in this multiple image region. But here the number of images that are found are 3. And then when it further goes inside, here now the number of images increase further. So there's the same thing now shown with another set of illustrations, where you can actually see the source with different colors, and you can see how how the source would look like in a source plane, and then correspondingly how would the images look like in the image plane. So I'll just go over this quickly. If you have this single source magenta, which is outside these caustics, then it's the one image. So if you can see here in the image plane, there's only a single image. And as it goes closer and closer, you can start to see that there are multiple images being formed. Similarly for the red, which is at the very much coinciding with the lens center, you can see the images being formed at different angles, and the number of images have increased. So here, this is again another illustration where you had this one set of source crossing these caustics from this angle, and here now the sources are crossing the caustics from the other angle, where it's now going through the what are called the cusps. So this just leads to different image configuration. So if you carefully analyze these kind of examples, then you can see there are some characteristic image configurations that one can see. So even by simply looking at the images, for example, let's look at this green source, right? This green source, which is falling on this part of the caustic. You can see that it is mapped in this following configuration, where you have this one image over here, second here, and the third and the fourth images, they are merging. They are, if you remember, they are closer to the critical curves, so that's where the magnification is really high, and you can also see very large distortion. So, when you see in lens systems, when you see arcs, these are the regions where the arcs are forming. So you can see here there are two images are merging, and the corresponding source location is like this. But now, if you look at the similar kind of like the green source here, but at a slightly different location in these caustics, here instead of two, now we have three images which are merging. So just by looking at the images and the configuration of these images, one can readily understand what kind of model this system may have, what kind of mass distribution, and how the source might be placed with respect to these caustics. So this is why it's very interesting and can be used as additional constraints in our modeling. So let me talk about a couple of simple lens models that people consider and analyze, and how they can be useful. So let's talk about point mass lens. So I'm showing here an example of a lens system. This is not a point mass lens, but I'm just showing it for the sake of illustration. So this is a sufficiently good example. So yeah, so let me just go ahead. So for a point mass lens, the scale deflection angle comes out to be this expression. And the corresponding, if you just substitute this alpha in the lens equation, right, which goes over here, then the lens equation looks like this for the point mass lens. And now imagine that the source is well aligned with the lens. So the source is right behind. So the beta, which is the angular source position, if you set that to 0, then you can rearrange this lens equation, and what you will get is this expression, which is called the Einstein radius. So what happens in this case is that when everything is put in here, the observer, the lens, and the source, for the point mass lens, the images are formed at all angles, and so what one sees is something like a ring, and this is called an Einstein ring, and the radius of this ring is the Einstein radius, and that's what is shown over here. So this basically gives us a scale of the system, overall scale of the system, and it mainly depends on the mass of the lens and also the distances, these angular diameter distances to the lens and to the source. So if you have a system like this, and if you can measure the distances, so if you can measure the distances with, from some observations, and the size of this ring can be readily measured from imaging, right? So if you can measure the size of the ring and the distances, then you can directly get very accurate measurement of the mass which is enclosed in this ring, right? And this is the total mass that you can measure from a lens system like this. And the point to note is that this kind of measurement does not make any assumption about the physics or any physical processes which are affecting the lens mass or the lens itself, right? This is purely geometrical measurement, right? And so this gives us very accurate measurement of the total mass which is enclosed within this aperture. And this allows us to get very an independent and accurate measurement of the dark matter mass compared to some other methods. So this is why lensing is very interesting. So I'll talk about that more in the second half of the talk. Yeah, so then the the observables we can calculate further based on these lens equations. We can calculate what are the image positions. So here multiple images are formed. So the image positions are given by this expression, and also the magnification can be calculated. So just to give a sense of the scales here, so if you look at this particular Einstein radius expression, and if you put some typical distance estimates, for example, like a few kiloparsecs for objects within our own galaxy, right? Then and also we use masses which are comparable to stars, right? So we get we get a roughly the scale of this Einstein radius to be of the order of the arc second. So this is the kind of estimates that Einstein had done, and because these deflections are of such a small angular scale, he had he never thought that we can ever observe lensing effect because these deflections are so small. But Zwicky was the one who knew about galaxy clusters, who knew that these galaxy clusters are much more massive systems, and he was the one who also had the foresight that gravitational lensing could be observed because of these galaxy clusters. So if you put in distances which are like a few billion light years away, which are the distances of galaxy clusters and so on. So these are in the gigaparsecs. right? And if you put masses of that of a massive galaxy or a galaxy cluster and so on, then the deflections are much larger, and so this is why it becomes possible for us to observe these systems. So next is the example of extended mass length. So these are the more typical systems that we can find. So these are the massive elliptical galaxies which are shown here. Some images are shown here. And so now we can recall again the deflection, which was the expression for the deflection, which was I suppose derived by Surhud in the last lecture. So now what happens for these kind of galaxies, we can assume this model which is called the singular isothermal sphere. So in this case, the density profile is given by 1 over r square, and the surface density in this case becomes 1 over r, which is given by this xi, which is the impact parameter. And this assumption of this isothermal indicates that the rotation curves, they are flat. So the rotation, the velocity, they are basically constant. And so in this case, if we now plug in this kind of surface mass density expression, if we plug in into the expression for the deflection, then what we find that the deflection angles for these kind of systems where the model is considered isothermal, we find constant deflection angles. And the corresponding expression for the Einstein radius is like this. So we can see again there is this dependence on the angular diameter distances and also the mass of the system basically. And we can also then further derive what are the positions of the images. So for all the positions where the source is within the Einstein radius, you can easily calculate the positions of the images. There are just two images, so the image positions are just given by beta plus Einstein radius and beta minus Einstein radius. And similarly, you can derive the magnification for these images as follows. So let me show you a few examples of one of the first lens systems that were observed. So here is an example. Here is an image of a twin quasar system, which was the first record of strong gravitational lens, confirmed strong gravitational lens. So this is an image of the Hubble Space Telescope taken from the Hubble Space Telescope. Of course, the original images were taken with ground-based, really small telescopes, so they didn't look as nice. So this was what is called the twin quasar system, and confirmed by Walsh et al. So initially they observed the system, and they found that these two quasars, they are very close together in terms of, if you just look at in the sky, these are separated by a few arc seconds. Okay, around 6 arc seconds or so. So if you look at the number density of quasars, the fact that these two quasars are so close together in the sky, and also they looked at the spectrum and looked at the redshifts, which were very similar. They could not initially they could not understand what could be happening, but the fact that they were so close together, it was hypothesized that it could be a gravitational lens. But for a gravitational lens, this 6 arc seconds happens to be a very large image separation. Again, falling back to the typical distances and so on, people did not know that there could be such massive systems like galaxy clusters, which could have sufficient surface mass density, and mass to cause such large angular separations. And so, even though they imagined this to be a lens, given the large image separation, it was kind of confusing whether this is really lens system or not. And so this is in the background is an optical image, whereas this is the radial image of the same system. And this further adds to the confusion, because you can clearly see that this is the image A and this is the image B. But you can see these kind of jets and lobes, radio lobes that you can see in image A, but then nothing is visible for image B. So again, because this is like the first system, it was hard to understand these are multiple images of the same source. If they are, then why are we not seeing the same features, right? So, but there were several studies that were conducted, and it was confirmed that this is the lens. So here is an example of one of the first lensed arcs, meaning background source is the lens galaxy, and where the lens is a galaxy cluster. So here also, it was interesting to see the historical development for this particular system, because so they saw this image of a galaxy cluster, and then they saw this really giant arc which spans in the redshift plane of the lens. It's corresponds to like of the order of 100 kiloparsec. And so you can clearly see by looking at all the other features in the images, we can see that the other galaxies, the typical sizes of the other galaxies and the morphology of the other galaxies, right? And so this thing looks like something very elongated compared to anything else that we see in that image, right? And so the question is, what are these features? Are they actually at the redshift of the cluster? Are they some? I mean, there were all sorts of hypotheses as to what this could be. Many of the claims were that this could be something at the redshift of the galaxy cluster, and there is some physical processes happening because of which there are some galaxies which are being tidally stripped, because of which you are seeing this kind of elongated features, or there are some interactions happening because of which there are all these bow shocks or some other features where you can see some remnants. So there were all sorts of ideas put forth, and many of them had this concept that these could be things happening physically at the lens redshift, causing these strange arc-like features. And then there were some of the papers by Paczynski and Kovner where they, I mean, even including the first paper, they confirmed that, or they presented the idea of this being a lens system. But these additional authors also added further support by making simple mass models for this system and how you can explain one single giant arc, because some of the cases that I talked about there, we can see multiple images, right? And so, and also the fact that this is so elongated, and looking at the curvature of the system and all those things, they took into account, and they said that it is possible for this to be gravitational arc. And here is a just like for a comparison, here you can see a HST image of this particular system, where you can very clearly see this spiral galaxy being stretched all the way. So this is also nicknamed the dragon because of its morphology. And so this is now again very visually captivating examples of gravitational arcs, and you can see many of these knots which correspond to the sites of star formation. So we can get very detailed view of this galaxy, which is at a very high redshift. So one can use these kind of systems to study the background sources. So now let me move to applications and talk about some of the applications in somewhat more detail. So let me start with the dark matter and what sort of how we can what sort of observables we can make use of to study the dark matter properties. So let me also say that I will not be covering all of the applications because there are too many, but I'll cover some of the major ones. So firstly, it's dark matter. So so we can so as I mentioned in the slide where I showed the point mass lens, how we can easily measure the total amount of matter by just looking at the location of the multiple images or the size of the Einstein ring and so on. So over the last several decades, people have found now hundreds of gravitational lenses. So we don't necessarily study one lens system, but we study a large sample of them. And so some of these works show large samples, the results from large samples of these gravitational lenses. So even though gravitational lenses are rare, because you need this chance alignment between the source and the lens, now since we have done so many large surveys, we have found hundreds of gravitational lenses, and we can do this kind of analysis. So these different colored points, they come from different surveys, different lens samples. And what is shown here in the x-axis is uh, the the mass of the lens system, the Einstein mass based on the lensing, right? And so what you can see is that so going from lower masses to more massive system, you can what you can measure is the fraction of dark matter in the system. So in addition to the, so as I was saying, in this system, like if you imagine a galaxy, then you have this dark matter halo around it, and then you have all the stars, right? So this is the simplest scenario you can imagine. So with lensing, you can measure the total matter, right? And from other studies, we can measure what is the mass in the stellar component. So that gives us the stellar mass. So in these studies, what we have done is we have measured the total mass from lensing, and then we have subtracted out the mass that is included in the stellar component, which gives us the dark matter mass. So that is then shown as a function of the total lens mass, and you can see that the dark matter fraction, it for lower mass system, the dark matter fraction is less, and for higher mass systems, the dark matter fraction is increasing. That it means that the more massive galaxies, they tend to have more dark matter in them, right? So this is shown as a function of the lens mass, and then here is another study where it is now shown as a function of the radius of the galaxy, or as you go outwards from the center of the galaxy, as you go outwards, how the dark matter fraction changes as this radial profile. And again, here you can see from smaller distance, smaller radial distances to larger radial distances, you can see that the dark matter fraction is increasing. Here is another study where a large sample of something like 150 or so lens systems were analyzed to consider different, again, additional physics which could be responsible to alter the dark matter profile. And so here two different models were considered, shown in blue and red, which say that either the dark matter which is present around these galaxies, either they are being affected by these stellar component, and meaning, so okay, so the red one is the case where there is no effect, the dark matter is pollutionless, there is no effect from the stars, whereas the blue component shows what if the dark matter particles, what if they are responding to the presence of these baryons or the stars, and how that will affect the dark matter profile. So here the dark matter fraction will also be affected, and so that's what is shown by these two sets of points, and this curve here shows where the observations are. And so this clearly then allows us to distinguish between these two models and allows us to understand what is happening to the dark matter in these systems. So now, so earlier I was talking about the fraction of dark matter and how it changes as a function of the lens mass or the radial distance and so on. Here now we're going to talk about the density profile, the mass distribution itself. So again, if you analyze hundreds of lens systems and try to understand how the mass is distributed, what is the radial density profile in these systems. So usually we assume a power law density profile for lenses, and so what we try to do is constrain the power law slope. So that's what is given by this gamma here, and for most cases, what we find is that the slope of this mass density profile, power law mass density profile, is close to 2, which correspond to this isothermal density profile which I talked about earlier. So here this is coming from this Koopmans et al. Study Each of these different curves show the density profile slope for each of the systems, but the red one is the joint analysis that is done on these large sample of systems, and you can see it's very close to value of 2. So this study is done for galaxies, and this is another study where we have looked at galaxy groups and galaxy clusters. So this is for individual galaxies, how the mass distributions are, but now we are looking at the mass distributions for much more massive systems where you have more than several tens of galaxies, right? And here this is a completely different way of doing the analysis. Here what we are doing is we are looking at again, we're looking at a statistical sample and we are calculating these, the sizes, you can imagine, like the sizes of the Einstein rings, or what you can say is are the image separations. So now suppose we have 100 lens systems, and then we determining how large are the Einstein rings in each of these systems, or how far are the images separated in each of the systems, and you just plot the distribution of those image separations, right? So that's what is shown here in these different colored data points. Okay, and these different curves, what they show are different models for the mass distribution. So this is for the entire population. Okay, so let us assume that our entire lens population can be described by, let's say, what is called the NFW density profile. Then how would the image separations look like? So that's shown by these red curve. Now, instead of NFW, if our lenses are all isothermal spheres, then this is how the image separation distribution would look like. Meaning there would be hardly any images with large image separations. And then there is a third density profile, which is shown by this, what I'm calling the total. This is some composite density profile. It's neither SIS, it's not, nor NFW, it's some composite density profile, which better represents the galaxy which is at the center of these galaxy cluster. Plus, it also accounts for the dark matter, because in these galaxy groups or galaxy cluster, dark matter contributes a lot, and so it is important to model both the central galaxy, which is basically stars or baryons, and then also the dark matter in the extended part of the lens system, right? And so this black curve is closer to how the mass distributions in reality, and this is also then evident by the consistency or the match in the predictions and the observations. So with this study, we could get constraints on the mass distribution of galaxy groups by comparing with these observations. So this was one of the first studies where we could do this using strong lensing and getting constraints on the galaxy groups, the mass distribution. Here I'm pointing out just a study where only one lens system was analyzed, but this is going even at a much larger scale. So now this is like a galaxy cluster. So in a galaxy cluster, we can combine strong lensing, and then there is also weak lensing. That is something that Surhud will talk about in the next lecture tomorrow. So here we have combined strong lensing plus weak lensing, and then so that's shown by these the solid and the dotted curves. Plus we are also looking at how the X-ray gas is distributed and what sort of mass distribution it implicates. And so here there is like multiple methods which are being used to combine to constrain the mass distribution of a galaxy cluster by combining all these different observations. So this particular case is for this. I mean, this is the lens system where this analysis was done, and what you can see is this. I think I showed this example before. What you can see is that there are these 4 images, but then there is also 5th image which is formed very close to the lensing galaxy, which is it's hard to see here, but it is present there. And once this 5th image was measured and we made use of these observations, we could get very good constraint on this stellar on this mass distribution, because we can see that these images, they are formed at different radial distances from the lens center, right? And so because we have additional measurement over here, which is very close to the lens center, we can constrain how what the mass or what the density profile must be in order to be able to produce this fifth image. Because in most of the cases or most of the lens systems that you will see, we actually see even number of images. It's either two images or four images. But there are only a handful of systems where we actually see an odd image, the third or the fifth image. So this is one of such exceptions where we can see this fifth image, which is very close, forms very close to the lens center, and it allows us extra observation constraints. And so if we have this kind of systems, we can better measure the density profile compared to any other methods. Many of the methods don't allow you to go to such smaller radii closer to the lens center. So this is another way we can make use of strong lensing. So the next is studying the nature of the dark matter itself, to understand what is the nature of the dark matter. So you may have heard that in this lambda CDM model, we assume that the dark matter is collisionless, but there are many other models which are also proposed, like Born dark matter, then there is self-interacting dark matter, and so on, to explain some observations, right? And so there are some instances where we can make use of, again, we can make use of lensing to put some constraints on these different models, like the self-interacting dark matter model, where we can, so for example, we can use a system like this. This is a bullet cluster you have heard of. It's a very famous system. Here, what happened was that they looked at this particular system where there were two clusters which were merging, and so the blue component here it represents the dark matter, which is measured via the weak lensing analysis, or weak lensing and maybe strong lensing analysis. And optically, you can see that there are lots of galaxies over here, right? What is shown in the red is the distribution of the gas measured from the X-rays. And so what is happening here is that there are these two clusters which have merged and crossed each other, but then the gas component is offset from the rest of the optical galaxies and also the dark matter. So these kind of systems, people have used this kind of systems to look at the offset between the dark matter and the optical galaxies and the X-ray or the gas component to determine how what is the interaction cross section of these dark matter particles. So suppose the dark matter particles are going to interact with each other, and when these kind of mergers happen, if we see some offset between the dark matter component and the luminous component, then we can put constraints on the interaction cross section for these SIDM kind of models. So this is one such system, and there have been a few other these kind of systems people have observed. Here I'm showing a slightly different case where we are looking at a system here which consists of multiple galaxies which are close together, and there is only a single gravitational set of images formed of a single background source. This is unlike this particular study, but it also helps you to measure this offset between the dark matter and the baryonic component. So here what is happening is that instead of in a typical system we have one single galaxy lensing the background source, right? Instead of that, you have a bunch of different galaxies which have their own dark matter halos, and they together are lensing these arcs. So when they modeled this system, what they found was there was an offset between the optical peaks that you're seeing of the galaxies versus the centers of the dark matter halos. So they again made use of this offset to understand and try to put some limits on how the interaction cross section for the dark matter particle. In all of these cases, there was not sufficient evidence or support for presence of self-interacting dark matter, but this just allows us to understand how we can use these kind of systems to to be able to say something about the nature of the dark matter. So now the other property that we can also look at is the abundance of the dark matter halos. So you may have again through these lectures you may have understood that the current model of structure formation that we have is this hierarchical model where we have smaller objects, smaller dark matter halos, which combine to form larger dark matter halos. So if you have a galaxy cluster which has which have a central galaxy and you have several satellite galaxies, they each have their own satellite dark matter halos, in addition to those, there are also other dark matter clumps which form pure dark matter only subhalos. So uh, from the standard cosmological model, we have some idea of what is the abundance of these dark matter subhalos given the mass of the main dark matter halo, right? And so again, for us to be able to measure these abundances of the dark matter subhalos, we can make use of strong lensing, and the way we can do this is by the fact that if there are, suppose, imagine now there are lots of dark matter subhalos, and now you have a lens system which is shown here, two examples of lens systems. So imagine now you have lots and lots of dark matter subhalos, and what will happen in these kind of cases where you have these multiple images, just by chance, some of these dark matter subhalos will fall very close to some of these lensed images, and they will cause further perturbation to the lensed image properties. And what are the properties that I mentioned? The image positions, the magnifications, and time delays, right? And so, once we had started to find lots of lens systems, there was a study by Dalal and Kuchanek where they observed, they analyzed a set of lens systems which seem to have peculiar properties. So the peculiar properties was that when you look at these different images and calculate their relative magnifications, they found that the simple models like the isothermal density profile kind of models, simple models could not explain the relative magnifications. There were perturbations in these images, and they attributed this to the presence of these dark matter subhalos. So a good fraction of these lens systems which were observed in the radio, they all seem to have what are called these anomalous flux ratios. That means the magnifications, the relative magnifications, were deviating from our expectations. And so making use of these anomalous flux ratio systems, they try to put constraints on the abundance of these subhalos, and they found that it is pretty much consistent with the cold dark matter model. So here these are the cases where only the flux ratios were affected. There are also other ways we can do this by looking at the positions of the images. So if the subhalos fall much closer to the images, then even the positions of the images can be affected, they can be perturbed. And so this kind of analysis was done by me quite some time ago. There was this substructure which happened to be very close to this gravitational arc, and by looking at the system in the radio at very high resolution, where you can see lots of features arising from the jet structure in these quasars, we looked at how the image positions of these different features in the jet, how they were affected, how they were perturbed. And with that, we were able to put constraint on the abundance of these subhalos. So there are other studies also which talk about how we can use high resolution imaging, where we can get milli-arc-second resolution for the positions of the images, and we can then constrain the subhalo mass function or the abundances by fitting models to these systems where we account for the subhalo properties and presence of subhalos in the system. So this was using these strong lensing magnifications and strong lensing image positions. Then there are other kind of systems where we can look at individual galaxy clusters. So because galaxy clusters are so huge and they have large lensing cross sections, a single galaxy cluster can have hundreds of background sources with their own families of multiple images. And so one can study these individual galaxy clusters by taking a high resolution and deep imaging and map out the entire mass distribution in their lens plane. Where because of these lots of arcs that are present, one can then get detailed um, model for how the mass is distributed. So this is what is shown by these peaks here. So we can get a detailed idea of how the on the substructure mass is distributed in the system. And so there was this one study by Natarajan et al. Where they mapped out this dark matter subhalo distribution. And again, they found that this is very much consistent with the standard model. All right, so now moving on to other kinds of applications. So apart from studying the foreground object, which is the lens, apart from studying that, we can also study the background object with the help of strong lens systems. And this is thanks to the lensing magnification, right? So because of lensing magnification, these systems, they act like natural telescopes. And what happens is that a very distant source, which would be very faint and harder to see in the absence of a lens, now we can see it with much more magnification, much more clarity, and thus we can study these distant sources, it will be galaxies or quasars, and try to understand the different physical properties of these systems, and we can then compare them with analysis or studies of similar galaxies but at nearby redshifts, and that allows us to then also get an idea of the evolution of these galaxies, because when we are studying these very distant galaxies, we are looking at we're looking at how these galaxies were very early on in their life cycle, right? So we're looking at how these galaxies were forming at very early stages and compare that with galaxies seen at late in the universe. And so here is a very vivid example of a gravitational lens system. This is probably one of the longest giant arcs that we have observed. So here again you can see that there is a background spiral galaxy with multiple images over here, another image over here. And this is produced by this galaxy cluster. What you are seeing here in the inset is a reconstructed model of the original source by doing a detailed modeling of the lens system. And again, because you can see with so much detail the structure in these images, you can make an accurate model for how the original source might look like, and this is what is shown over here. Yeah, so this particular system, the source is at a redshift of 1.7. The total magnification, this is 42 roughly. The extent of this arc is around 40 arc seconds. And so, when you have this kind of extended sources and complicated mass distributions, the images that one can see are also not very simple. So what is happening, because the source is very extended here, some part of the source, it falls in the 3-image region, which I had shown earlier with these caustics, right? Some of the image, the source, because part of the source falls in the 3-image region, the corresponding images are seen, only 3 sets of images are seen, and the other part falls in the 5-image region, and so we can see 5 images of the other part of the source. So this is what is shown here and found in this particular system. So here I'm showing some results from Sharon et al. And other collaborators, White et al. And so on, where they have looked at further detail into this particular background galaxy to study the velocity dispersion, the age profile, and the metallicity profile, and the surface mass density, and so on, to better understand the star properties like the star formation rate, what are the sizes of the different clumps that you can see here, what is the metallicity in these galaxies, and so on. And this is just a teaser shown here. As you know, the JWST has been launched a couple of years ago, and we have been seeing all these very fancy and beautiful images, and some of the striking images or analysis that have been done are forced from gravitational lenses. And here is one such image of a galaxy cluster where there is quite some strong lensing features that you can see. Over here, for example, you can see this massive, like a big galaxy in the background. So one image is over here, and there are two images over here produced by this central galaxy in this cluster. Then there are additional set of images shown over here and here of a different source. So here, for example, you can very clearly see that this arc, which just happens to by chance be very close to some of the other satellite galaxies, you can very clearly see all the distortions that are happening, like in the image positions of the arc. It's not a nice curved arc, but it has all these wiggles and features. And then another interesting thing, you can see that because this galaxy happens to be again at the end of that arc, now that single image of the arc is split into two arcs. So this is the effect that I was talking about using the subhalos or the satellite galaxies, where you can see additional deflection or perturbation produced by substructure in these systems. And so what happens is that not only you can get with the help of this giant arc, not only you can understand the mass enclosed in this region, but now because of this additional splitting of the images, you can also get very accurate measurement of this satellite galaxy. So these are the kind of interesting things one can do with massive galaxy clusters. And I don't know if it's easy to see or not, but there are additional arcs over here. There are many interesting features in the system. So this is taken with JWST, which is mainly in the infrared. But I'll just show you for comparison how the HST image look like, which is more on the optical. So it's not just a direct comparison between two telescopes. It's also the filters which can highlight how the intrinsic spectral energy distribution of different galaxies can look like. So here in the optical we don't really see much. So you see all these yellow circles, they point to that reddish galaxy, but it's hardly visible in the optical over here. But let me flip between the two images, and now you can see the difference, which is partly coming from the fact that we're looking at optical versus infrared, but we can also see how powerful JWST is and how the kind of resolution one can get in these lensed galaxies. This is a big image that I've shown, but if you actually look at the image up and close, you will see there is a lot of details in this galaxy which will allow us to study in great detail the morphology and star formation properties for this distant galaxy. So yeah, I mean, we can look at some other features. Like for example, there are some. Sorry. Yeah, let you go. So there are some other galaxies which don't even show up in the optical images, but you can clearly see again here and here. You can very clearly see in this infrared image taken with the JWs. Right. So some of the other applications are, for example, you can make use of lens quasars to get some idea about the properties of the black holes which are hosted in these systems. So you can look at the scaling relations. So, for example, there are theories which try to explain what are the black hole masses we see, and in what kind of host galaxies we expect to see them, and how these massive black holes can be formed, right? And so to be able to answer these kind of questions, we want to look at the relations between the host properties and the black hole property. And so people have tried to measure the black hole masses and then correlate it with the host properties like its luminosity, the total luminosity or the bulge luminosity, and so on. But with lens quasars, what we can do is that because of the lensing magnification, we can look at much more distant and fainter quasars and get constraints on these systems and allow independent constraints on these kind of scaling relations. So next I want to talk about cosmology. So I talked about how we can study the foreground lens properties and the background source properties through lensing magnification. The third major area of application is cosmology itself. So, let me this animation made by Surhud. So we can imagine that there is this background source, and then there is a supernova that goes off. And suppose that source is sufficiently well aligned with us, the observer. Then what will happen is that the supernova will also be strongly lensed, and you will see multiple images of this supernova, right? And so because it's a transient source, we can measure the time delays in this kind of systems. And as I mentioned earlier, through the time delays, we can get some constraints on the cosmological parameters like the Hubble constant. So this idea was first presented by Repsal in the year 1964, and he talked about lens supernovae and then how we can do this. So it was amazing to think of these kind of possibilities. But the chance of seeing a lens supernova is very rare because finding a supernova itself is rare, and then finding something that is lensed or multiply lensed is even more rare. And so historically, it so happens that instead of lens supernovae, we have been making use of lens quasars to do what Refsdun was predicting. And so over the several decades now, there have been various collaborations like Cosmogrill, Holy Cow, and now Pele Cosmo collaborations who have put humongous efforts in trying to do long monitoring observations of lens quasars where we can monitor the variability, like I showed earlier in an animation, right? How the over a period of several years, you can see that there are these fluctuations happening in the quasar, and we can then measure the time period. So these are some examples of the lens quasars which were studied in these collaborations. And this is a snapshot which shows latest results from these collaborations, showing the constraint on the Hubble constant. And these are then also compared with other independent measurements of the Hubble constant to better understand the universe. And so the advantage of these lens quasars is that they are much more abundant compared to lens supernovae. They are just there for us to study. But the downside is that these quasars, they have variability, intrinsic variability, and it takes years and years, sometimes decades. One has to follow up these systems for decades before we can actually measure these features in the light curves and get sufficiently accurate time delays to be able to get sufficiently accurate and precise constraints on the H naught. So in that sense, while they are many more in number and easy to follow up, but the observations themselves are extremely painstaking, and so in that sense, it is not as interesting. Whereas these lens supernovae, so these are the systems we have just recently started to find from some of the surveys like the Zwicky Transient facility, which are dedicated to finding transients. And so these surveys are now started to find, and there are going to be even more surveys like the LSST and Euclid and so on, which will allow us to find many more transients, and also as a result also many more instances of lens supernovae. So if I just give a quick snapshot of the status of this field, about like a handful of lens supernovae that we have found in the literature. And I think one or two, and the interesting thing about type-A supernovae we know the intrinsic luminosity. These are the only, I mean, because we know the intrinsic luminosity, we can determine what is the absolute. So this is not possible for other lens sources where the true source flux is not known. But for type 1 supernovae, we know how bright the intrinsic source is. We observe how bright the lens supernova images look like, and then we can infer what is the absolute lensing magnification factor. So this gives us additional constraint which is not possible with other lens systems, and this is the main advantage of making use of lens supernovae. The other advantage is because it's a transient source, we don't have to monitor necessarily for decades to be able to measure the lensing time delays. So these are some of the advantages of having lens supernova. But the downside slightly is that these lens arcs which are formed, or the lens supernovae which are seen over here, which are very close to the galaxy, the lensing galaxy, because the presence of these stars in the foreground galaxy, they produce further perturbations. So this effect is called the microlensing. So on top of the strong lensing, where you see multiple images, on top of the strong lensing, which is because of the main lensing galaxy, there is further perturbation arising because of all the small stars which are present in the galaxy. And so this added complication makes it kind of difficult to make use of the lens supernovae to do cosmology. So, but still, this field is very promising, and it's upcoming. We hope to find many more lens supernovae, and the complementarity of lens supernovae with lens quasars and also other probes, supernovae themselves for cosmology, right? So the complementarity means that it is still interesting to study these systems to get improved constraints of cosmology. So I'm going to show here a few slightly different ways which allow us to study cosmological parameters, but by looking at a statistical population and statistical properties. So not individual systems, but by looking at a large number of lens systems. So this idea has been around for a while now, which is based on the abundance of giant arcs. So the idea is that the presence of these giant arcs are basically seen in very massive galaxy clusters. And so, based on the number of or the abundance of galaxy clusters, we can infer the number of giant arcs that can be seen. And if you look at the abundance of the galaxy clusters, or the model for structure formation, it tells us that the number of very massive galaxy clusters are very few. So very massive systems in the universe, they are much rarer. And so if you consider different kinds of cosmological models, they predict different number of these massive galaxy clusters. So by looking at the abundance of these galaxy clusters, we can put constraints on the cosmological parameters. So this is what was suggested by Bartley and al, where they looked at different cosmological models here, like open CDM, lambda CDM, and so on, and made predictions for how many giant arcs one would see as a result. And in their initial analysis, they found there was a huge discrepancy, that the difference between the predictions and observations were a factor of 10 and so on, which triggered lots of studies, lots of studies to understand where the discrepancy is coming from, and whether lambda CDM model is really consistent with observations or not. Over the decades, people have done much simulations to predict the giant arcs, and also the observations have become better. And right now, there's hardly any discrepancy that is found. Basically, we find that these abundance of giant arcs, they are kind of consistent with what we expect from lambda CP. Then there are other statistical studies which make use of the image separations, which I talked about earlier. But in my earlier case, I was talking about how we can constrain the dark matter properties by looking at the image separations. Here, the image separations of lens quasars is used to now uh, 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 put constraints on the cosmological model itself. So this is for different model of the dark energy. If we change this omega lambda parameter, how the expected image separation distribution vary, and then we can now compare it with the observations to be able to say something about the dark energy itself. So similarly, so this I think this is just the same result, where we show simultaneous constraints on the dark energy equation of state W and the omega matter, and then so that's shown in the red, which is also then compared with other cosmological probes. So then finally, I want to show this one very interesting system, kind of system where we can again make use of this strong lensing to get cosmological constraints. So I've been talking about an observer and a lens and a source, but there can be even more rarer instances where you can have multiple sources being lensed by the same lens, or there could be multiple lenses in the line of sight to a single source. So this is the idea of these double source plane lens systems, where you have one observer, you have a lens plane, and then you have multiple sources that happen to be there in the line of sight of a single galaxy. For galaxy clusters, you always have multiple sources, so that is not that's nothing unique. Here, this is a unique space where we can have multiple sources behind the single galaxy. So this kind of systems, if you have this kind of system, so we have distance measurements not only to one redshift plane but also another redshift plane. And so in these cases, what happens is that we are able to measure two, instead of one Einstein ring. Now we have measurement of two different Einstein rings, and through that we are able to. There was an image, but okay, maybe not. With the help of these measurements of these two Einstein rings, we can constrain the cosmological parameters through these distance ratios which enter into the calculation. And what we find is that there is no dependence on the Hubble constant, but instead we can constrain other cosmological parameters like the dark energy equation of state and omega matter. So this is in the red, what we are showing is from a mock sample of a few lens system, how the cosmological constraints will look like. And here is a real example of a double source plane lens system observed with the Hyper Super survey, where you have this lensing galaxy which is in the foreground, and then this arc, you can see this red arc which is the first source, and then you can see this blue like feature which correspond to a more distant source at a different redshift. And so this was one of the first spectroscopically confirmed lens double source plane lens system that we had found, and then we did some analysis to understand how exactly we can have this kind of morphology, and to better understand the source and the lens itself. So with this, I would like to end and leave just a slide of references with the help of which I had prepared these slides. So you may want to refer to this material in case you are further interested in studying on this. So thanks a lot. Yeah, so please feel free to
Question in chat.
So the question says, can the perturbation like supernova in a lensing galaxy have any effect on the images? I'm not sure what exactly this question is referring to. Maybe what Sumit is trying to ask is that if you have multiple lensed images, if the supernova goes off in a lensing galaxy, okay, the supernova is going on in the lensing galaxy, right? So whether the supernova goes off or not, the presence of a star or multiple stars in the lensing galaxy will have effect on the images. That's what I was referring to when I said microlensing. So the the physical process where the supernova is going off, that in itself does not have any direct implication. Maybe to some extent, not really that much. So, but the fact that there is a supernova or there is a star or there is additional structure in the lens galaxy will have effects, perturbative effects on the lens images, either in the form of affecting the magnifications or affecting the image positions and so on.
How does the brightness of the images change with the lenses?
So when we talk about the magnification that is happening both in the flux, and also the area of the image is also changing similarly, and so the surface brightness of the image is then conserved. That doesn't change. It's the area which changes and also the flux which changes.
So if we get a bigger image, then it would be too dim.
No, it would be brighter. Both they scale similarly, and so the flux divided by area stays the same, whether it's the source or the. So that's actually the other property which one can look at while studying lens systems. That these multiple lens images that you see, their brightness should be conserved. So based on the distortions that you see, based on the sizes of these images, the flux to area, flux over area should be similar in principle.
Can we derive the mass of neutrons using supernova and
Mass of the neutrons. Sorry, you mean neutrons? Okay, mass of the neutrons using the
supernova? Like if we see a galaxy which is gravitationally dense and we observe it some period of time. So like shouldn't we see a landscape of neutrons from a supernova?
So, you mean the neutrons and neutrons? What neutrons you are talking about? You mean?
I'm talking about the gravitational lensing, like we can derive the mass of neutrons from gravitational lensing and supernova.
So you're saying the neutrons are present in the supernova.
We can see. Like I don't like it sometimes. Make me confused also after the space.
Maybe you're talking about neutrinos.
Yeah. I'm also confused, but I will answer again.
Okay, please check what you had read. Yeah.
What is the way to counter the Hubble, the most fluctuation in Hubble constant? Is there a way to manage, we can get the accurate Hubble constant instead of the fluctuations? It is 67 flow per second megaparsec to 75. Is there any way of getting it?
So see, in observations, in any kind of measurement, there will always be uncertainty on the measurement of any parameter. So what is your question? Is your question that which method we can use to get more accurate constraints? Is that what you're asking?
Yes, yes, yes.
I think, I mean, one can look at the various observation probes that people are using to measure the Hubble constant. I think there are different probes which might give more accurate constraints at different redshifts, and also the uh, as our experiments get better and better, as our telescopes get better and better, then we expect to see improvements in the uncertainties from individual probes. So it's maybe it's not so straightforward to answer this question. Any other questions?
So, in the second application, then, the first application, I remember that it was about measuring the fraction of dark matter for different mass systems using gravitational. And in the second study, I remember it was about like based on distance and some radius, like in the x-axis it was something like radius, and we are measuring mass fraction.
Fraction of dark matter.
This you mean?
Yeah, yeah.
Remove this chart.
So
Can you see? Oh,
so in the first one, I can understand that we can have different like objects that are like gravitational objects. So we can get this data in that way. But what is the distance here? Like distance
is
from
the radial distance from the center of the lensing galaxy as you go outwards.
okay, so we need to have like different objects that are having different radius, and we are
Yeah,
getting
yes.
all the results from.
Correct. Yes.
And one another question was like, if we try to measure the redshifts of the images, like, is there any changes in the color of the images from the lens? Like, is there any kind of frequency changes or color changes from the image, from the source image?
No, we expect the colors to be the same. The lensing effect does not affect, in principle, again, it does not affect differently as a function of the frequency, except what happens is that if your lens itself has masses at different scales, and if your source also has structure at different scales, then you may see some frequency dependent effects. But if you just have a smooth source and a smooth lens, lensing doesn't allow any change in the lensing effects as a function of frequency. So one should not see difference in the colors in principle. And then there are also some line of sight effects that happen, like in the line of sight to image 1 versus image 2. There could be some dust or gas in the line of sight of one image but not in the other. And then there could be absorption and scattering and those kind of things. So in that sense, practically you will see or you may see difference in the colors, but from lensing itself, if you have a single scale involved, then you will not see.
Ma'am, what is the physical meaning of determinant of Jacobian going to zero? Are source plane, image plane in the same line?
That is just so here it corresponds to the source which falls on this caustics. So this is this is the region where if you solve the lens equation, if you calculate the Jacobian matrix, there the determinant will go to zero. So the source falls in a specific region where the images like if you do the lens mapping, then it will correspond to very high magnifications. So
the image gets like stretched in one direction, the other direction goes to like 0. So, so that is like formally. It's like you are changing the and still the beta. Sorry, it's del beta by del. Yeah. So you change theta and still beta does not change.
Looking at lens quasars to find the model function, don't we need some kind of variation to actually measure it? What kind of variation?
So these are intrinsic variations happening within the quasar itself. There are these different. So there is a black hole, and then there is this gas which is accreting uh, in the vicinity of the black hole, and it emits X-rays, or it also emits light at other frequencies, optical and so on. So there are all these physical processes, and also there are these. If you look at the model of these quasars, you see apart from the gas which is being accreted, there are these what are called the broad line regions and then narrow line regions. So there are various structures where, and the presence of these gas and clouds which which absorb certain light and scatter and so on. So there are many physically it's a very active system where you see intrinsic variations in the fluxes as a result of this gas being accreted. Okay, if there are no questions, then thank you so much.
I'll see you tomorrow.
Final lecture on this.
Recording stopped.
Tomorrow. For example, background source may not emit light from the same part of the source at a given point. So, for example, let's talk about the quasars, and the X-rays are coming from gas which is being emitted, right? The entire system is not emitting X-rays. It's coming from certain part of the source. That region of the source has some physical sense, right? And so when you look at those caustics, it might fall, let's say, into the image region. Then the images that will form are whatever double image or 2 images or 3 images or something. And now if you look at the optical